base dimensions, like length, mass, or time, can be combined to make derived dimensions. So if you have a base quantity like length and a base quantity like time, you can combine those to do distance over time to give you a speed, which are going to have dimensions of length per time. So you might write this as length per time with these brackets to indicate that you're talking about dimensions. You might combine those into one, length per time. You might write that as a length to the first power and a time to the negative first power. Lots of ways of expressing the same sort of thing. So why do we mention this? Well, there's a handy tool, which is checking for dimensional consistency. So any mathematical equation relating physical quantities has to be dimensionally consistent, which means that any term that you're adding, subtracting, or equating has to have the same dimensions. It also means that anything that's going into certain mathematical functions, like trigonometric functions, sine and cosine, tangent, logarithms, or exponentials, have to be dimensionless. So they have to have no units on them for this to work out. I think this is easiest to see with an example. So we will check the dimensions of the quantities in this equation that I'm going to show you to see if it's dimensionally consistent. So here's an equation. Velocity is equal to v naught, so initial velocity plus 1/2 acceleration times time squared. V equals v naught plus 1/2 at squared. Is this correct? Well, checking dimensional consistency won't necessarily tell me it's correct, but it can help me determine if there's some problem with it. So let's look. We can look up velocities. That'll be a distance over a time. So this will be a length per time for velocity. This velocity is also length per time. And now we've got some quantities over here that we have to look up. So we've got an acceleration. This ends up being a length per time squared. And a time. So that's going to be a time. And then the squared, ends up squaring it. So we can check those dimensions and say our velocity is length per time. Here it's length per time here. And over here we have length over time squared times time squared. The 1/2 is just a number. It doesn't have dimensions associated with it. And so we'll notice that the time squareds here will cancel. And we're just left with this, saying that a length per time is equal to a length per time plus a length. And right here, we note that it's okay for lengths per time to equal, but you can't just add a length to that. So this says that this must be incorrect. Why? Because that doesn't match up. And you can think about it like this. I can add 10 meters per second to 15 meters per second, right? Or I can add 1 inch to 1 centimeter. I have to do some unit conversions, but it works. They're both lengths. But what is a meter plus 3 miles per hour? It doesn't make any sense. Or a meter plus 2 meters per second, right? Here we have a length like a meter, meters per second. You can't add them. It doesn't make sense. It's not dimensionally consistent. So checking for dimensional consistency, again, doesn't necessarily tell us that it's correct if we do get consistent units or consistent dimensions. But it does tell us when we get inconsistent dimensions that it is incorrect. And I'll add on that a lot of people find this easier to do rather than doing lengths and times and things like that. Find it easier to do with actual units. So if that's you, feel free to do that. You can substitute in and just put like meters per second squared, multiplied by a second squared. These cancel, you get meters, right? You can do it with units. Just be aware when you're doing units, just use base units for whenever you're plugging in things. Don't use like kilometers or whatever, just meters the whole way if you're doing that. And that should get you through. I have one more note I just want to mention. It said dimensional analysis earlier, and we are analyzing our dimensions here. But dimensional analysis can also refer to determining how certain system parameters might depend on other parameters, giving like by looking at the dimensions. So there's Rayleigh's method of dimensional analysis. There's the Buckingham pi theorem you can look up. So feel free to look those up and explore those. Here we were just checking dimensional consistency. So the dimensional analysis, there's another term that sometimes gets used for this. And this actually kind of neat stuff as well. But they're related but slightly different concepts here.